what is this talk about? Right, so what I really want to do is to introduce this generalized stochastic localization process, and in some sense that should be the main topic of the talk. But before I can introduce the generalized process, it makes sense to introduce the non-generalized process. So in some sense, a lot of the focus will be on what is stochastic localization, and it will probably be better to do it with some motivating question in mind. So I'll start by presenting a motivating question which relates to some spectral graphs for measures on the cube, and mostly for decompositions of measures on the cube. So mostly one way to think about it, it's a new way, or one possible way to take a measure on the cube, which can have almost arbitrary complexity, and decompose it into simpler measure, and simpler will depend on the setting. So that's kind of the plan going forward. Yes, and everything I'm going to talk about is joint work with Ariana Piana, who's currently a graduate student at the Weizmann Institute. Okay, that's the general plan, and I'm not sure how the interaction is through the Zoom, but feel free to stop me at any point if you have any questions. Right, but so I said I'll start with a motivating question, and here is the motivating question. I want to define a measure on the cube, and it is a measure of the following form. It has a quadratic potential. Okay, so J is a matrix, and the measure is defined simply by the action of by treating the matrix as some quadratic form. And I'll always implicitly assume that the matrix is positive definite. There's no loss in generality here, because I can always add a diagonal, and that only accounts for a constant for inputs on the cube. Right? They have a constant norm. One way to think about those measures is as if they assign magnetism or interactions to particles, right? So if you're on the n-dimensional cubes, we have n particles, and magnetic particles. Each one can have plus magnetism or minus magnetism, can have their own spins. Right, and there are interactions between the different particles. So the entries of the matrix determine the interactions. Okay, if there is a positive entry in row 1, column 2, then there is a positive interaction between particle 1 and particle 2. Their spins want to align, and if there is a negative entry, then the spins want to to reflect, to have different values. And of course, if there is no value, if the entry is 0, then they do not interact directly, but they can interact through neighbors. Okay, so that's one way to think about it, as determining configuration of particle system. But you can also think about voting dynamics. You have a list of voters. Each voter can either decide yes or no, and they affect each other, right? Either two voters think alike, or they want to vote, in opposite directions. So you can define, you can represent a lot of natural systems using this model. It's called well, I mean it originates from Ising's works on magnetism, so it's sometimes called the Ising model. And a basic question which pops to mind is, given such a measure, how can you sample from it? How can you sample a configuration on all the particles or on all the voters according to that measure? So, right, I mean, there's a general paradigm to sample from any given measure, basically, which is to construct a Markov chain, which has mu as its unique invariant measure. Start the Markov chain from any arbitrary state, evolve it, And well, as time goes to infinity, the law of the process converges to the unique invariant measure. So you just need to run the Markov process long enough, and you'll get you'll get something which has the same or a distribution which is at least very close to mu. So, I mean, we want the sampling to be efficient. So we need two things. We want to be able to design a Markov chain which is easy to implement, in the sense that it has simple iterations. And then we also need it to mix fast, right? We don't want to run it for many, many iterations. So at least the first part, a simple Markov chain on the cube, is easily implementable. That's true for almost any measure, right? That's sometimes called the heat bath, or Glauber dynamics, or the Gibbs sampler. I'll call it Glauber dynamics now. And it basically goes in the following way. You're at a given state at time t. You want to progress forward to the next step at time t plus 1. You have n coordinates in your state. Choose one randomly and update only that single coordinate. How are you going to update it? Take the measure you want to sample from, freeze all the other coordinates, and sample the new coordinate according to the conditional distribution. Right, so it's pretty easy to check that mu is the unique invariant measure, simply because it has all the correct marginals, or all the correct conditional marginals. And in the case of the cube, this is very easy to implement. At every step, you're just flipping a coin, right? Because every coordinate is just supported on -1, 1, and you can easily calculate the conditional distribution. It's just the bias of the coin according to the potential, to the quadratic potential. So it's really easily implementable. You just need to evaluate the quadratic function. But the question is how efficient, how many iterations do we actually need to run for that Markov process? Okay, what is the mixing time basically? And we want to separate between a mixing time which is polynomial or even linear in the dimension. Right, I have to flip at least n coins if I want this thing to mix, but I don't want to mix to flip more coins than that, and running times which are exponential. So that's a very general setting. Before we dive into the general setting, let's see a simple example. And I mean, if that's the first time you hear about the Ising model, it's a nice example to see. So that's the simplest interaction matrix you can take. It's a rank 1 matrix where, it's just the all ones matrix. So all the particles interact with one another. You can think about it as interactions on the complete graph. All the interactions have the same intensity, and all the particles want to have the same spin, basically. Right? So the matrix with all ones, we normalize it by n, so that it will have a fixed operator norm. The operator norm is 1. And beta is a parameter we can play with. The smaller beta is, the less interaction there are, right? When beta is 0, then all we see is a product measure. There are no interactions, and product measures are very easy to sample from, right? When beta is large, you expect the measure to decompose into two states, either the all ones or the all -1s. So the process won't even be ergodic for beta infinity, okay? And the question, what happens in the middle? Okay, now there's a very easy way to analyze that specific measure, or what Glauber dynamics, what the Markov chain, how the Markov chain evolves for that specific measure, because even though it is a measure on 2 to the n states, really everything is homogeneous. So I don't need to keep track of the exact state I am in. It's enough to keep track of the potential, right? It's enough to keep track on how many ones are in my state, because everything is invariant to permutations, right? So for simplicity of analysis here, we can, start from an arbitrary state. Let's say that we started from the all one state. All particles have a positive spin, whatever that means. Okay. And instead of looking at the entire vector-valued Markov chain, let's look at the, people sometimes call it the magnetization chain, but it's a one-dimensional Markov chain, which is just basically we're going to count how many ones do we have as opposed to how many minus ones. And we can normalize that. That's not very important, right? So xt is on the cube. When you take its inner product with the all ones vector, you get something which is between minus n and n. You divide by n, you get something which is between -1 and 1. And each time you flip a bit, which is what you'll do at every step of the Glauber dynamics, well, either you don't do anything, or you increase your total count by 2, or you decrease your total count by 2. Right, so it's so the transitions are pretty easy, right? It's pretty easy to describe the transition, and basically we can write them as a function, right? The transition only depends, well, they depend on beta. That's the only parameter we have, and it's depend on the current position of the Markov chain. There are only three possibilities: either at a given magnetization level, at a given m, we stay fixed, or we move 2 steps to the right, should be probably 2 over n, or 2 steps to the left, right? So let's call p the move to the right, to the positive side, q to the negative side. Let's take the ratio. That's p over q. And you can write it. It has an explicit expression, right? It's just a function of beta and m, the magnetization. But in some sense, this ratio, it measures how strong of a drift we have towards the positive side. The bigger it is than 1, the stronger the drift is to the right. The closer the smaller it is below 1, the more negative the drift is. Right? So now we can plot it. Here are 3 plots. This is for small beta. So when beta is equal to negative, so when beta is equal to 0.1, we can see that when the total magnetization is positive, the drift is smaller than 1. So there's a very strong pull to the left, right? So positive states want to become negative. Something very, very different happens for large beta, right? When beta is equal to 1, or yeah, in that case, when beta is equal to 1, we can see that in some positive states, the drift is larger than 1. So there's a very strong pull to the right, which means that if the process starts from the all ones vector, this is represented by being 1 here, it will always see a drift to the right, and it will never be able to cross 0. Well, not never, but it will take exponential time for the process to cross 0. Right? So for the total magnetization, it will take exponential time to cross 0, which means that it cannot mix, which means that the entire process, the original process, the Glauber dynamics cannot mix. So there's a qualitative difference between small beta and large beta, and you can see that there is an exact phase transition happening at beta equal 1/2. Right, that's when you have a critical point at 0. And you can actually take that on observation and make it into something very precise and rigorous, and that goes back to the 60s. And that's the statement that if you take the Curie-Weiss model, that's what he just presented, when the interaction matrix is the all ones, and you run Glauber dynamics, then it mixes rapidly. It mixes in nearly linear time, if and only if beta, that parameter, is smaller than 1/2. And if it is larger than 1/2, it will take exponential time to mix. Right? So that gives a very, very clear characterization of that sampling procedure. Now, it's not true that Glauber dynamics is the only way to sample from that measure, right? It's pretty simple. So you can think of other sampling algorithms which will work in any regime. But I mean, that's the motivating question we have for now, okay? So there are 2 takeaways from the example here. The first takeaway is that we should expect to see some phase transitioning happening in those models. You know, when something is small, when there are not a lot of interactions, we expect the measure to behave like a product measure, which makes Glauber dynamics very efficient in sampling. When the intensity is very large, when the interactions are large, there should be some possibility of structuring into different states of a measure, which will make sampling very hard. And there should be some sweet spot in the middle where we see a phase transition. Okay, that's the first takeaway. The second takeaway is more philosophical, and it's we were able to completely analyze and characterize that measure because it was simple. Right? I could just write everything explicitly. And well, the moral here is that simple things are simple. Okay, simple things are tractable. And we shouldn't expect that to be the case in general. Okay, so in some sense, when we want to handle general interactions, somehow the idea will be to reduce it into simpler models. Okay, and there's some ways to carry out that reduction, but one way which was very successful goes through stochastic localization. Okay, so very super brief introduction to stochastic localization. I mean, it's a stochastic process developed by Ronen Eldan to study basically the KLS conjecture, but since then it's been proven useful in lots of different settings. And the basic idea is to take a complicated measure and decompose it into a mixture of simple measures in a tractable way. Okay, I'm not saying a lot because you didn't say what I mean by simple, and I didn't say what I mean by tractable. Okay, but one thing to keep in mind is simple means the following, or could mean the following thing. Take your original measure, it's mu, decompose it into a mixture of measures, and those mixture of measures are tilts of mu by a Gaussian factor. Okay, so Q is a positive definite matrix. So we take the original measure and we tilt it by some Gaussian factor. Now, the idea is that Gaussians are nice. We understand Gaussians well. And if the original measure, mu, has some nice properties, then when we tilt it by a Gaussian, those properties only become better. So that's a very vague sense of being simple. But that's something to keep in mind. Tractable means that we can apply stochastic tools of stochastic analysis to analyze it. Okay. Right, so that will probably be the most technical slide I have. That's the formal definition of the stochastic localization process. I mean, don't if that's the first time you're seeing it, don't try to remember everything here. I'll try to highlight the important points. But the point is that it is a measure-valued process, right? And we want to define a process of measures. Instead of defining the measures themselves, I'm going to take a process over the densities. Okay, so F, it's the density of the measure relative to our reference measure mu. At time 0, it's just 1, so the original measure is just mu. And we evolve it along time. Okay, so at time t, ft is another density, which we multiply by mu. Right? So if ft really is a relative density, we'll just get a new measure. Okay, and how is that process defined? Right, it satisfies some stochastic differential equation, whatever. Basically, what we do at every step, we take our original measure, ft, or original density ft, and we add to it, right? That's the differential. So that's the term we add. We add ft times some linear term. Okay, that's a linear function of x. It has a random slope. Okay, bt is a Brownian motion, but think about it as a small Gaussian, so a random direction. And we have two parameters we can play with in the definition. One is that's a matrix CT. it determines basically the volatility of the Gaussian, the covariance of the Gaussian. The other one is AT, right? It is the intercept of the linear function. So let me explain the two roles of AT, of AT and CT. Those are the important things here. So CT I mean, it's a matrix process. It defines the covariance, but what we really use it for is to encode linear constraints in the process. Okay, and I will show kind of an example of that in a second. The details are not super important, but the point is that we can encode linear constraints in some form using CT. Okay. AT, it's a vector. It plays a more important role. For now, we always choose it to be the barycenter of the measure at time t, right? It's the expected value of mu t, ft times mu, that's exactly mu t. Now, that's an important choice because, you know, we just define a process of functions here. I want it to be a density function. I want them to define measures. So they need to satisfy two things, right? Well, they need to integrate to one and they need to be positive. It turns out that choosing AT as the barycenter is the unique choice which forces the function to integrate to one, right? And here is an easy way to see it. I mean, the way to see it, right? That's the total mass of the measure at time t. And we know that at time 0, it's equal to 1 because it's a probability measure, right? So if we stay a probability measure at every time t, the differential of that better be 0. So let's calculate the differential of that. Well, mu t is just ft times mu. Let's take the differential inside. Well, that's exactly, I mean, we just plug in the expression we have here. And we get that because AT is the barycenter, we just get something which is 0 almost surely. So the differential is 0 almost surely. Total mass does not change, and it just stays 1. Okay? I didn't say that the density is positive yet, but it is positive. And one way to think about it is we're basically defining a logarithmic derivative here. Right? We can divide both sides by ft. On the left side, we'll get the differential of the logarithm of ft. And the logarithm is will just be some linear function. So to get an expression for ft, now you can integrate and exponentiate. So when you exponentiate, you get something positive. And again, you can actually make that into something rigorous, except that when you integrate Brownian motions, or when you take derivatives of Brownian motion, there is a quadratic term. Right? So this is an actual expression for mu t, or rather the density of mu t. Right? It's what you get by exponentiating and, by integrating and then exponentiating. Except that because there's a Brownian motion, there's also a quadratic term. Right? That's what we get from the quadratic variation of the Brownian motion. So something pretty cool happens here now. Right? Because of the quadratic variation, we can collect terms. Right? So if we just open the brackets here for the norm, we'll see this matrix to the square, and then we integrate it. So that's a quadratic form, which is a Gaussian factor. And we can collect all the other terms, but all the other terms only depend linearly on x. So let's call it LT, which is an affine function or a linear function. And we really get just our original measure times some Gaussian tilt. And as t grows larger, this matrix here also becomes larger. So the variance of the Gaussian tilt shrinks over time, and we're really localizing the measure into a smaller and smaller area. So that's why we call it stochastic localization. Right. So how to use such a process? Let's go back to our example of Glauber dynamics and the Ising model. We want to show that Glauber dynamics mixes rapidly. whenever you have a Markov chain to show that it mixes rapidly, I mean, that's equivalent to showing that it has a small spectral gap, right? Or in other words, that it satisfies a Poincare inequality. That if you take any test function phi and you measure the variance of phi with respect to our measure mu, that will be smaller by some constant c times the Dirichlet form associated to the Markov chain. Okay, I won't write the exact expression for the Dirichlet form of the Glauber dynamics. It won't play any role, but it's something we can write. Okay, so I want to prove that mu satisfies a Poincare inequality. So remember, in the stochastic localization process, we had AT, which encodes, which is the barycenter, which ensures the measures remain a probability measure, and we had CT, which allowed us to encode some constraints. Now we can use it, and I wanted to encode the following constraint. Okay, maybe we wait. So the point is that when we define it that way, it's just something times a Brownian motion. Okay, so everything is a martingale here. There are no drifts, which tells me that if I'll take any function, right, mu t itself is a martingale. If I'll test it against any function, I'll again get a martingale. Right? In particular, the process if I check the L2 norm of the test function phi with respect to the measure mu t, that's a stochastic process, it's a martingale. But when I calculate a variance, I need to subtract the expected value of phi square of the expectation. That is a sub-martingale. Okay, it's no longer a martingale. What we can do is we can encode a linear constraint into CT, which forces this term to stay constant. Right, that's a linear constraint in the space of measure. I force this expectation to stay the same along the process. Right, that the only possibility for a sub-martingale, the only possibility for a square of a martingale to also be a martingale is if the martingale is constant. So if we force this expectation to be the same all the time, we get that the variance is a martingale, and this will be very useful in a second. The other thing we do, we can make sure that the image, that the row space or the column space of C is always contained in the column space of our interaction matrix J. Right, so that when I take J and I subtract that integral of CT, I'll see a decreasing process, which is valued in positive definite matrices. I can make sure it decreases, but never decreases below 0. Now, because I added a constraint to CT, I'm losing some rank. Okay, I'm losing some degrees of freedom, which means that I can ensure that this thing will be strictly decreasing as long as its rank is at least 2. Once the rank is 1, I don't have enough degrees of freedom, and maybe the process just stops at that point. Okay? So I'm being kind of vague, but I'm trying to illustrate the things you can do with the matrix, or the things you can encode in it. Now, why is this useful? Let's define a stopping time for the process. We know that this matrix decreases as a process of positive definite matrices, of interaction matrices. It decreases as long as it has rank at least 2. So let's look at the stopping time when it reaches rank 1. It's strictly decreasing, so eventually we will reach rank 1. And let's ask what happens to the process at that time. Okay, so we wanted to bound the variance of phi with respect to mu. We made sure that the variance with respect to mu t is a martingale. So the expected value of that martingale is just the starting point at time 0. And the measure at time 0 was mu. Now, suppose we knew that at time tau, at the stopping time, all of those measures satisfy a Poincare inequality with a uniform constant, right? Let's call it C. So you can just apply the Poincare inequality point-wise to every integrand here inside the expectation. And then there's an easy argument which basically uses concavity of the Dirichlet form, which allows you to go back to the Dirichlet form of the original measure. Right, so if I can bound the constant C here, I'll prove a Poincare inequality for the original measure. And explicitly, what is this constant C? It's the worst Poincare constant among all measures of the following form, right? It's exactly what we had here. Some linear function and some matrix. But the matrix is what we obtained from the process JT, which is decreasing when it collapsed to rank 1. So R must be of rank 1 at time tau. And, well, it's smaller than J because it's a decreasing process. So the operator norm could not increase along the process. Right? So we took an arbitrary problem and we reduced it to simple problem. Right? Very explicitly, those are the types of measure we need to handle. A rank 1 matrix, we can write it as simply an inner product squared with respect to the rank 1 decomposition. So those are simple measures. And we just saw that simple measures are easier to analyze. So it turns out it's pretty easy. Well, I mean, there are a lot of tools to prove spectral gap for rank 1 measures, for interaction matrices which are rank 1. And this is basically what you get. And that's rather sharp. So if you combine all of those things together, you get a result of Ronen Eldans, Freddy Kohler, and Ofer Zaytouni from about 4 years ago, which tells you that if you take a positive definite matrix and the operator norm is at most 1/2, otherwise this thing won't make sense, then this is exactly the spectral gap. This is the Poincare inequality you get, which also shows that you have a rapid mixing of Glauber dynamics. Right, and if we look back at the example we had about the Curie-Weiss model, about the all-ones interaction matrix, this is exactly the same threshold we had, which showed that this result is tight, at least in that sense. But it was also useful for other things. For example, you can take an interaction matrix with Gaussian entries. GOE, it's also called the Sherrington-Kirkpatrick model. And then, I mean, it gave pretty good result there. But the point is that everything here really crucially relies on the matrix, on J being a matrix, right? So it's not clear whether it is generalizable to, to other types of measures or to other types of interaction. Yeah.
Is there a converse in this theorem?
Oh, in what sense?
Oh, just if I'm remembering the result about Curie-Weiss, there was this if and only if.
Yeah, so for Curie-Weiss, it's an if and only if. And here it's definitely not an if and only if.
So there's no like partial converse or something that says.
So the converse is there is a matrix whose operator norm is larger than 1/2, and Glauber dynamics does not mix fast. But there is also a matrix where there are plenty of matrices where their operator norm is larger than 1/2, and they do mix rapid, and Glauber dynamics does mix rapidly. Yes.
And it's like not understood more deeply what in that large operator norm regime.
So there are some deep open questions. I mean, yeah, for example, if you take J to have just independent Gaussian entries, it's not clear what happens above 1/2. That's an open question, for example. Or if you take J to be negative definite, then just push it to be positive definite. That's also a problem. So there are a lot of open things there. Yeah. So what happens above that is, I mean, it's a Wild West. It depends on really is model dependent.
Thank you.
Yeah.
I have maybe a question too.
Yeah, sure.
So the bound is type basically for rank 1 matrices, and this shows also in the proof that the worst Poincare constant is attained at rank 1 matrices. So I mean for J being rank 1.
So when J is rank 1, we think about J rank 1 is definitely the worst case.
So could there be some kind of stability result where if J is far from being rank 1 in some sense, then you can go above this threshold of 1/2? Because okay, in the trivial setting, if J is like full rank, I mean, if J is a multiple of the identity, you're just doing nothing, and you can see if J is rank, like is
Terrific. I don't know how to answer that in general, but I do know that you can take full rank matrices and not be able, okay, I don't know that, but there should exist rank 1 matrices which shouldn't allow you to go very far beyond 1/2. Right, so maybe you can get to 2, but not beyond that. But a general stability result, that's a terrific question. I don't know. Yeah, can you find a matrix which is far from rank 1, whose threshold is at 1/2? I don't know. That's a terrific question. Yeah. Any other questions?
Yes, I want another one which is a bit related. So in the example where J is this like the priori model, I guess the covariance explodes as well at 1/2.
Yes, that's true.
This regime which are known, where the Poincare constant is not comparable to the, say, the operator norm of the covariance. Or could it be
So the Poincare norm bounds the operator norm of the covariance.
I'm asking if like the reverse bound, like sort of the KLS reverse bound, is possible in the regime where J is less than 1/2.
So it's true. It is true that when are you asking if there is a reverse bound when J is larger than 1/2?
No, smaller than, like if there is a KLS bound for CP in this regime, if it's possible or not.
Yes. If you okay, almost. I mean, what I basically, okay, I didn't show it, but if you can bound not the covariance of your original measure, but of linear tilts, right? If basically no linear tilt makes the covariance too large, then you can get the reverse. So it's almost. So the question is how much can a linear tilt destroy your covariance? And in some sense, you don't expect linear tilts to ruin the covariance because they just push you in one direction. Yeah, so that can actually be made precise. If your measure is very stable with respect to linear tilts, then the covariance stays small, and there is rapid mixing. And you can actually use stochastic localization in slightly a different way to show that. And so that's a good point. So maybe I'll mention something about that soon. Yeah. I hope I answered your question.
Yeah.
Okay. Right. So the point I'm trying to make is that we were able to use this decomposition into rank 1 matrices to handle quadratic interactions. But now what happens if we have something which is non-quadratic, right? What happens if 3 particles or 4 particles interact directly, right? So I mean, there's no sense in running the process. The entire point was that we started with a quadratic function. We subtracted a quadratic function from it, and we could game the system to make sure we end up at another quadratic function, which is easier to work with. If J is not quadratic and we subtract a quadratic function from it, I mean, we won't get anything. Well, I mean, we will get something, but I definitely can expect it to collapse to a rank 1 matrix because it's not a matrix, right? And maybe just to drive the point further, why did we get a matrix here? Because we had a Gaussian tilt, right? We took our measure, we took a Gaussian tilt. The Gaussian tilt corresponded to subtracting a quadratic function. And we got that Gaussian tilt because a Brownian motion has a quadratic variation. So, a natural question is, if we have higher order interactions, can a similar technique work? Or equivalently, can we induce non-Gaussian tilts in a useful way, at least? Okay, and that's what I'll talk about for the rest of the time I have. So let's just go one step further away from matrices. Okay, 2 steps actually. So instead of considering quadratic forms, let's consider quartic forms. I'm skipping cubic. It will become maybe apparent soon, but in some sense, the simplest thing after quadratic is quartic. So degree 4, I want a degree 4 polynomial instead of a degree 2 polynomial. Formally, instead of taking a matrix, let's take T. T is a is a degree 4 tensor. And then we'll take the most pedestrian view about tensors. We'll think about them as operators on matrices. So a degree 4 tensor takes an n by n matrix and returns an n by n matrix. So we can really think about it as an n squared by n squared matrix, right? That's really the most pedestrian view of tensors. And now we have a measure of the following form, right? Mu, which is its potential is T of x, right? T of x, it's just the tensor evaluated at x. Or if we think about it as an operator on matrices, is applied to the rank 1 matrix of x, then take the inner product back with x times x, right? So basically we evaluate it at x. So the most natural thing to try is simply to repeat the same arguments we had for with the stochastic localization process, right? Run a process of measures, but instead of working with linear functions, we'll work with quadratic functions. Okay? And we need again to choose AT, and now it won't be a vector valued process, it will be a matrix valued process because we're working with quadratic functions, but we'll simply choose it in the correct way to ensure that that everything remains a probability measure, to make sure that the differential of the total mass is 0, right? So we can just write the differential of the total mass, and that's how we choose AT. It will be a vector, and we choose AT to cancel it. And well, now to make sense of that, those things are matrices, so the thing on the right of the inner product should also be a matrix. So instead of taking a Brownian motion, we'll take a Dyson Brownian motion, which is a fancy way of saying a symmetric matrix with independent Brownian motion entries, right? So just more randomness, but really it's the same thing when you flatten it to a vector. And MT is, well, it's a degree 4 tensor because it's an operator of matrices, right? So we can repeat the exact same things. We can still think about it as a logarithmic derivative, so we can integrate and exponentiate, and we'll get the exact same formula. The only difference is that we have a quadratic function instead of a linear function. Right? So instead of seeing x, we are seeing x squared. But it really is the same formula as before. Right? And we can expand it. Right? So that was the relative density with respect to mu. Then we have t here. Well, now we have a square of a degree 4 tensor, but we think about degree 4 tensors as operator on matrices. So we get another degree 4 tensor, and we can game the system to make sure that t minus that thing eventually collapses to a rank 1 tensor. And we're happy because everything works the same. Except there are two problems. Right? That was too naive. The first problem is the term we have here. Previously, when we had it, it was a linear term. Right? It was LT times X. Now it's a quadratic term. Previously, for mixing, we really didn't care. Right? LT times X was tilting by some product measure. That doesn't affect what Glauber dynamics is doing. Okay? In other settings, you tilt by a linear function. It's convex and concave. I mean, it really won't affect you. Here, I mean, it's quadratic. LT could be positive definite, could be negative definite, could be neither. It's not convex, it's not concave. LT could be very, very large. I mean, provably the spectral gap can be large. For example, if LT happens to be the all ones matrix. Right, so the first problem is that it is not linear in X, and that could really make the spectral gap large. The second problem is that we were too simplistic, right? We treated T as a matrix, as a very big matrix. So when it will collapse to rank 1 thing, it will collapse to a rank 1 operator on the space of matrices, not to a rank 1 tensor, right? That was too simplistic to hope for. So it will collapse to something of the form D tensor D, where D is some matrix, not to V raised to the 4th power. And I know how to handle spectral gaps of that thing. Handling spectral gap of those tensors is, I mean, it's not obvious at least. Right? So how to handle those two problems? So I'll start with the first problem. Let's try to remember what is LT. We got it, right? We collected all the terms which only here depend on X tensor X. So all the linear terms from before. So if you write it explicitly, that's the form LT has. It depends on A, right? A is that vector which ensures that, well, now it's a matrix, which ensures that we always have a probability measure, plus some random term which depends on the Brownian motion. My problem is that it exists. But really my problem is that it is large. So if I want to make it smaller, the first thing I can do, I can remove A. Right? I can just remove A and I automatically made it smaller. Now, in essence, that's a problem because maybe I won't get a probability measure now. But I can encode more constraints into my matrix M. Okay, right? Remember, previously we encoded that the expectation of some test function remains fixed. We can add another constraint, just that, well, the expected value of 1 remains fixed. So we're delegating the role of that barycenter process to a constraint in the matrix. Now we have 2 constraints. So we made this matrix, we made this term smaller, but there's still a Brownian motion here. It could still be arbitrarily large. That's not good enough. But the point is that now that we've removed AT, we have some flexibility in choosing it again. So instead of working with AT, we'll introduce a new process, VT. Right? such that if I write here VS instead of AS, I get a new vector and I can make it arbitrarily small. Right? So somehow the question is reduced to something in stochastic analysis. Given a martingale, can you always choose a drift to make sure that the process stays small? It doesn't leave a small ball around zero. So, I mean, if you think about it, if you take M to be the identity matrix, it's not a hard problem. And it turns out, right, because it's just a Brownian motion, and can you always just push a Brownian motion in the correct direction to make sure it doesn't leave a ball, right? So you just add some drift, which gets stronger as you get to the boundary of the ball. Turns out that if you add some matrix and that matrix is not too large, which is our case, you can still do it, right? So it takes some stochastic analysis shenanigans, but it's doable, right? So for any reasonable matrix process MT, you can choose a drift to make sure it is as small as you, always as small as you want. Right, so now we can define the stochastic process in the following way. Instead of having the barycenter here, we have that drift, which ensures that the quadratic term is arbitrarily small. And MT now encodes for two linear constraints. It ensures that the variance stays a martingale, and it ensures that mass is preserved. Mass is always one. Right, so now we can do the exact same thing, except since I have less degrees of freedom, because we're encoding for two constraints. So again, I have this decreasing tensor valued process, TT, and it decreases, and I can make sure it keeps on decreasing as long as it is of rank 2, not rank 1. I have two constraints, so I can only expect it to collapse to a rank 2 element. Right, but at that time where it does collapse to rank 2, we have the following expression, right? So it doesn't collapse to a rank 2 tensor, unfortunately. That's the second problem we had. It collapses to a rank 2 operator on matrices. Right, so we can write it in the following form. We don't have that, bad term LT, but we have a rank 2 element of the following form, right? Which explicitly is there are two matrices, D1 and D2, and that's how we decompose our measure. And those matrices have a bounded norm because we obtain them from something which decreases, right? So they are bounded by the tensor norm of T. And we don't have any immediate results for spectral gaps for those types of measures. So we need a way to decompose them further. Right? We really want to work with low rank tensors and not low rank operators on matrices. But the point is that by now we can just repeat the exact same ideas. How to do that? We can simply iterate, right? So we have that the measure here. Well, right, we can separate it into two copies. I mean, that's not really separating, right? I'm simply writing a square as a product of something with itself. We can freeze everything, and then run the same process on one copy. Right, and again, we have two constraints, so it will decompose into two things. Right, it will decompose into a rank 2 matrix. And the second copy remains fixed. So now I'll run the process again, but now on that copy, so it will decompose into a rank 2 matrix. So basically, now I have here two rank 2s, here I have two rank 2s. When I take their product, I'll get 4 rank 1 tensor, or one rank 4 tensor. And I can repeat it for the second matrix, and I'll end up getting, instead of a rank 1 decomposition, a rank 8 decomposition. Right? So I started with an arbitrary tensor, we decomposed it into two matrices, then we decomposed the matrices into rank 1, and we ended up with 8 different vectors. So again, now we have Now we have measures of that form. They're represented by rank 8 tensors. And you know, by following the exact same step as before, it's enough to just understand the spectral gap of those measures. And those measures are simple, so we can understand their spectral gap. Okay? And that leads to the following result. I mean, in that specific case for rank 4 tensors, where if you bound the norm of the tensor to begin with, and it is smaller than some constant, then you can get a bound on the spectral gap, which leads to rapid mixing. Unlike the case for matrices, unfortunately, this is not this. Okay, I don't think it's sharp. I think we're missing by a factor of 8. Right. So that fact that we needed to use 2 linear constraints, and eventually that percolated into having 8 different vectors, made us lose by a factor of 8. It's slightly more complicated than that. I know that the suboptimality is slightly better than 8. Right? We just showed you that case for tensor is not as easy as matrices. But it's pretty close. Okay, so we can actually bound the suboptimality. We don't know exactly what is the suboptimality, because I know, but we can guess what it is, and it's slightly better than 8. And we can apply it to other models, of course. So if T is not arbitrary, again, maybe T is a Gaussian tensor that leads to a spin glass model. We basically lose another constant factor, but we get pretty close to the conjecture threshold. And what to a conjecture threshold, and basically what I described here is mostly for rank 4 tensors, for degree 4 tensors, because that was the simplest non-trivial case to describe. But the ideas, you know, they work beyond that, so they can also work for higher order tensors, or for what people call mixed spins. So maybe it's, a degree 4 tensor corresponds to a homogeneous polynomial. Maybe I want to handle non-homogeneous polynomials. So the method does have, at the moment at least, some constraints. Right? For example, I don't know how to handle degree 3 tensors, because everything here relied in a very artificial way of thinking about the tensor as an operator from matrices to matrices. So a degree 3 tensor is an operator from matrices to vectors, or from vectors to matrices, which doesn't mean that there isn't some easy trick just to embed it into to a larger space and make it work. But yeah, at least what I described right now won't work for degree 3 polynomials. And maybe one last comment to connect back. So in the matrix case, as I mentioned, and as I was asked, if you have a bound on the covariance matrix, you can transform it actually into a bound on the mixing time. And you can try to do the exact same thing here, except it turns out that what you need here is not a bound on the covariance matrix, but rather a bound on the appropriate moment tensor. So, for example, in the Sherrington-Kirkpatrick model, if we could get, that doesn't matter for the tensor-Curie-Weiss model, if you could get a bound on higher moments rather than the covariance, then we do know how to translate those into bounds on the mixing time using stochastic localization. But those things seem to be much harder to get than bounds on the covariance. Okay, I think that's what I wanted to say. So thank you for listening.